Okay, so firstly, thanks to the organizers for inviting me. Um, so this will be two talks. So on sharp phase transition and noise sensitivity and continuum percolation. I hope to start with the basics of some little bit of continuum percolation and then move on to sharp phase transition in the first talk and then noise sensitivity in the second talk. Okay. Um, Okay, so firstly, is a joint work with Giovanni Peccati from Luxembourg and Guenter Last from Karlsruhe. Just about managed to do the important part. We could visit him, Giovanni and Guenter, before the entire lockdown started. Just lucky with this. Okay, so let's get started. First part, I'll introduce something about continuum percolation, then say what is mean by sharp phase transition. And even though I'll be stating a new proof of an existing result, I will point out what is the easiness in this proof. Okay, what makes this proof much simpler. And we will see also, I'll point out about further results, further applications at the end of the talk, depending on time. Okay. So let me say the first thing I want to say is just let's get the model set up correctly. So the basic object here is the Poisson Boolean model. So what is it consisting of? We first have a Poisson process. Poisson process is a set of points in RD. I always take D greater than or equal to 2. Okay, I take the dimension to be larger than or equal to 2. And lambda to be, lambda is a parameter. It's the only parameter here, the simplest model. So lambda is finite. And what does it mean to say, what are these points? These are random points scattered in the plane. I will show some simulation shortly. But what is the important property for us if you have not seen a Poisson process? Here is what you should keep in mind is that if you take any bounded subset of the plane, if you take any bounded subset, the number of points is given by, there are a Poisson number of points where the parameter of the Poisson random variable is lambda times the volume of W. It's a bounded subset, so it's finite. So this is a number is Poisson random variable and the points are uniformly distributed on the set W. Okay, so you take a bounded subset W, you put IID uniform points and the number is random. Okay, Poisson process, all it means is that when I look at any bounded subset, there is a random number of points which are put uniformly and IID. Okay. And now what do I do? To each of the points, I attach a radii or a, for me, the radii, I call Ri to be the radii, but essentially what it means, it's again, it's IID, Ri's are IID with a distribution Q, which has a compact support. Okay. So I take a compactly supported distribution, say the support is 0 to R0, and these are non-negative random variables. And I attach each Ri to an Xi. Okay. So there is this quantity, I call it the Mark Poisson process, or in general, the Poisson process with the radii. Okay. So this is what is a Mark Poisson process. It has each point as a mark. And now the Boolean model is simply, I take Ri to be the radii, put balls of radius Ri around each Xi. I put balls of radius Ri around each Xi and take their union. Okay. So this is, I call it C of lambda. Remember, I will use this notation many times. C of lambda and eta. Now onwards, can forget eta tilde, but eta and C of lambda is something which will keep coming often. Okay. And now something very particular in this is what is the C0 lambda is the component. C of lambda is a subset. It's a subset of RD. So it can contain origin. If it contains origin, the component that contains origin is C0 lambda is the component that contains origin. If it does not contain origin, I set it to be empty set. Okay. So this is C0 lambda. It's the component containing origin if it exists. Now let's just get some very simple simulation. Okay. So one mistake with notation, this is eta tilde. So this is the Poisson process, a simulation. It's actually, I put the journal to also indicate that, this Boolean model is not just a mathematical curiosity, but it's some very useful in many applications. And so this is from a journal on applied vegetation science. Okay. So these are Poisson points. The first figure shows the Poisson points in a box. And the next one shows balls of random radius centered at these points. And in the third, you just forget the balls and you forget the centers. You look at only C lambda. The white region is the C lambda. The white patch is C of lambda. Okay, you do not know the centers or anything. You just see C of lambda. Okay, and I have highlighted C0 lambda is a particular patch. Okay, it's C0 lambda is the patch containing the origin. Okay, so this is a simple simulation of a Poisson process and the Boolean model. Okay, and this is what we are going to be concerned is about this white patch in the last figure. Okay, how large is this white patch? How does it look like? Or rather, how large is main question, in particular C0 lambda. Okay, so what are the questions in this model? So again, just to recollect, C lambda is the occupied region, what I call the occupied region. And the main question is C0 lambda, is this unbounded? Okay, the first basic question is C0 lambda unbounded. How large is it? Okay, if it is bounded, how large is it? If it is unbounded, when is it unbounded? For what values of lambda is it unbounded? And how large is it when it bounded? So this was a very simple model and introduced by actually Gilbert in 1961 to study communication networks. Okay, and since then has been used in many things. And in particular, it's a very classical thing. You can see there are two references, one by Rahul Roy and Meester and Roy, and other by Bolabash and Rioda, which both contain the basics of the model. Okay, so highly recommended if you want to learn more about this. And now Rahul is giving a course as well, in which probably you will see you can have slides and everything. So this has been in various other books. There are various things, but it's a very well studied by now. But still, it seems that one can show a lot of things, and there are a lot of interesting things here. Okay, so this is the model. Let me mathematically define about unboundedness, how large, all that. Okay, someone sent a direct message. So aren't both the centers and radius coming from compact sets? The points are not in a compact set. I'm saying that restricted to a compact set, I can describe it cleanly. Okay, I'm not describing it in the entire space, but I'm saying that all that is important to understand is that we are always going to be worried about things in a compact set. Okay. So this is saying that restricted to every compact set, it behaves like this, but there are points in the entire space. Okay. Okay. But of course, every question will be defined many times on a compact set, and then we will let the compact set grow. So very simply, for example, the main event often, the more general event is A connected to B in C lambda. That is there a path? Is there a path? If you see here, all I'm saying is there a path from a set A to B consisting of points in C lambda? Okay, consisting of whether I can go from A to B via C lambda, the occupied region. This is what we denote by this. We will see specific A's and B's which are of importance. The first important A and B is when A is a singleton, origin, and B is a boundary of a ball of radius n at origin. So A is a singleton, origin, and B is the boundary of a ball of radius n. So all this means is that from origin, can I find a path that goes up to a ball of radius n? Okay, that is all this means. That can I find a path from origin going up to a ball of radius n? Okay, and so you can write it in different way. Also say that the component at origin intersects the boundary of the ball. Okay, whichever way you want to write it. This is theta n of lambda. Okay. And as n increases, this is decreasing. So it converges to theta of lambda, which is there an unbounded path from origin? So 0 to infinity means that there is an unbounded path, and this is the probability of percolation for me. Okay, theta of lambda. And clearly theta of lambda is increasing in lambda. Okay, as lambda determines how many points I have in the space. If lambda increases, theta of lambda is increasing. And so immediately what one can see is that there is some lambda c below which it is 0 and above which it is positive. And in the very first work itself, Gilbert showed that lambda c is non-zero, non-infinite. Okay, lambda c is non-degenerate. So I won't be telling you the proof of this. Okay, many of you would know. I won't be saying anything about how one can show lambda c is finite. There are nice arguments for it. But anyway, let's take it for the moment that there is a finite lambda c which is not 0, such that theta of lambda is 0 below that and positive above that. That is, the probability of there being an unbounded path is 0 below lambda c and strictly positive above lambda c. Okay. Okay. Now let me introduce some tools and put together how I can understand. I want to understand when theta lambda is 0, how fast is theta n lambda decreasing to theta lambda to 0? How quickly does theta n lambda decrease to theta of lambda? This is what I'm interested in. Okay, so let me speak about this next and introduce how does one prove it classically and what do we try to do. Okay, this will be the major part of the talk. Okay, so the rest of the talk will be focused on how can I show how fast is theta and lambda decreasing to 0 when lambda is less than lambda c? What are the key things and what is the reduction we obtain? What is the simplification we managed to do? Okay. So the first tool in this, a very crucial tool, is what is known as the Margulis-Russo formula in the discrete setup for IID 01 random variables. It's known as Margulis-Russo formula. But for the Poisson process, was shown by Zuev and Molchanov. Okay. Okay, so there are some variants of it, so I attribute it to both. Zuev showed one of the first versions, Sergei Zuev, and then Molchanov and Zuev together had some improvements. So we used more the later at some part. Okay, so theta and lambda, I can differentiate it with respect to lambda. Okay, so the derivative of theta and lambda with respect to lambda has a very, very neat formula. What is the formula? Theta and lambda is expectation. So I've written here everything. Theta and lambda is the expectation of Fn of eta. Fn is the indicator. I go from origin to a ball of radius n. Fn is the indicator function of interest. Theta and lambda, it's its expectation. I take a derivative of this. It turns out to be expected, what is called the add-1 cost of the first Malayavin derivative, okay, of Fn of eta. And what is Fn of eta? Remember, eta is the Mark Poisson process. Fn of eta is nothing but I add a point x comma r to eta. That is, I add a point at x with radius r. I add a point at x with radius r, okay, to eta, and look at the difference. Sorry, this should be Fn, okay. So Fn of eta is nothing but d, the derivative, the Malayavin derivative, or the add-1 cost. Okay, this is called the add-1 cost. Let me keep it. I will use it again. So the add-1 cost, I can always, it's written as, it's defined as adding a single point, okay, x comma r, and looking at the difference. Okay, how much does it change my functional Fn? How much does my functional change? And then take an expectation and integrate over the radius r and the location x. Okay, So this is what it is. And this turns out to be the derivative of theta n of lambda. So very nice. Q is the distribution of the radii. So Q is the probability distribution of the radii. Okay. And the next important tool is the Poincare inequality. What does the Poincare inequality say? It tells that the variance of Fn, which is theta n lambda into 1 minus theta n lambda. Fn is an indicator random variable, so it's a Bernoulli. So variance is p into 1 minus p, theta n lambda into 1 minus, is upper bounded by lambda times similar integral as above, but with a mod square. Okay. This is with a modulus and a square. But note that the mod square does not matter here because Fn is 0, 1 valued. Fn is 0, 1 valued. So the Malevin derivative, the add 1 cost is also taking values in 0 and 1. Okay. So the add 1 cost takes values in 0, 1. It uses 2 points. One thing to notice, actually, I didn't mention in this case, this is non-negative as well. By adding a point, I can only increase the chance I have a path. Adding a point only makes the chance of having a path better. If I didn't have a path in eta, by adding xr, I can only have a path. I cannot destroy a path. Okay. So this is always non-negative and takes values in 0 and 1. So which means the mod square is same as without the mod. So now you can easily combine 1 and 2 and get this inequality. Okay. So you get this differential inequality d theta n by lambda by d lambda is greater than or equal to this. Okay, you get this differential inequality. So I'll just let it be there for a minute. There is this inequality is not quite the inequality we needed. Okay, so the inequality we need is an inequality of this form. This is the inequality we need. Okay, that is d theta n by lambda, one extra factor c of Sn by n. I need this extra factor in the inequality. Okay, if you can get this extra factor, okay, where Sn is nothing but the integral of theta s of lambda from 0 to n. So this is the key inequality we are looking for. We somehow want to get this Csn by n, okay, in the inequality. Suppose we can do this. Then, very, very nice. I'm not going to give a proof of this. It's not a hard proof. You can see the paper of Dumnil, Kopa, Raufi, and Tassion, which motivates a lot of our work. That if you have a differential inequality like in star, all you get is immediately for lambda less than lambda c, theta n decays exponentially fast. Okay, this is actually the easier part somehow. Okay, but the harder is to show that actually above this it goes to positive. Okay, the proof, okay, I'm not going to say anything about the proof or explain it, but it's by analyzing this differential inequality and doing some bootstrapping, that getting a stretched exponential decay and then an exponential decay. Okay, so I'm not going to explain this again. We will be only concerned with inequality star. This is a key inequality to remember. How do I prove an inequality like this? Okay. Okay, so this inequality or variance of it was known, or people have proven this theorem is known already. So you can find a version of it proved in Meester and Roy. That is statement 1. I'm saying when I say 1, it's the exponential decay. So whenever I say exponential decay, I mean this statement. For lambda less than lambda c, it decays exponentially. Okay. So 1 is proved in Meester and Roy. You can see it's the classical argument of Menshikov from 1986. Then a newer, simpler proof of 1 for bounded shapes, not just balls of radius, but bounded shapes, was shown by Sebastian Zichter, student of Guenter Last, which adapted a different argument of Dumnil-Kopa and Tasio, much simpler than Menshiko's proof, okay? And using a refinement of a branching process argument. This is Zichter's thing in 2018. And then Dumnil-Kopa, Raufi, and Tasio came up with an even simpler proof. Okay, I mean, I would say idea, not a proof, was slightly different. They proved even when you have a radius, not bounded radii, but radii decaying exponentially, that is my radii distribution Q has unbounded support, but with exponential tail decay, they showed a result of exponential decay using renormalization arguments, okay? So this is a result already known in various forms, but I'm going to give a proof which is much simpler, and then I'll talk about, generalizations. Okay. So what is our strategy? Is that we are going to prove the differential inequality by improving the Poincare inequality. We will improve the Poincare inequality using roughly what is called randomized algorithm in discrete setup, and then come up with a good algorithm, okay? This strategy, I will make it more clear, is inspired by 3 papers of Dumnil-Kopa, Raufi, and Tasio, which really popularized this use of randomized algorithms in proving exponential decay. And as I keep telling now and then to some friends, ever since Dumnil-Kopa, Raufi, Tasio wrote these papers, there has been an exponential increase in the number of papers proving exponential decay. Okay, before that, you never got self-contained proofs. People would refer to Menshiko's argument and then refer paths. But after Dumnil-Kopa, Raufi, Tasio, there has been a dramatic increase in number of papers proving exponential decay. Okay. Why do we care about exponential decay? Why do I care about exponential decay? Here is some very quick this thing. Why is exponential decay important for us? So there are 3, I can define the critical threshold in multiple ways. Okay, one is the expected cluster size is infinite, and the other is, forget the second one, if you have not seen it before, it's something which is very useful in renormalization, is the probability of going from S to 2S ball. Probability of going from a ball of radius S to 2S, okay? Does this probability, is this uniformly bounded below? Okay, so this is what is the second intensity, that when is this positive. The third is what we have seen already. Okay, we have seen this already. This is the one we defined, what we defined. Okay, trivially, if this probability is positive, the expected size is infinite, not a problem. Okay, so lambda c tilde is less than or equal to lambda c. Similarly, lambda c hat is also less than or equal to lambda c. If I have an infinite component, I'm always crossing any ball from S to 2S. Okay, I'm always crossing a ball from S, I'm going to 2S all the time. Okay, you have a path here. Okay, so trivially, these 2 inequalities are true. Using exponential decay, you can show that these are all equal actually. This is a big this thing in having exponential decay, that you can show many critical intensities are equal. You can look at the book of Mister and Roy. There are many more. So I look, refer to Mister and Roy for many more such inequalities. Okay. Okay. So now I'm not going to discuss more consequences of exponential decay. I will show how do we get exponential decay. Just to recollect, we want to prove the inequality star with this extra factor. So it is enough to improve the Poincare inequality by getting a factor Cn by n. Okay, let's say constant Cn by n. If I can improve the Poincare inequality by getting this extra factor. Poincare inequality didn't have this factor. Okay, now if I get this extra factor, then I'm done. And because of my property of this dx being in 0 and 1, okay, the add one cost being 0, 1 valued and f being 0, 1 valued, whether I take the mod square or mod, it does not matter. So I will prove the second inequality. Okay, we will prove this inequality. This is the inequality we are going to prove. Okay. What is the key tool in proving this inequality is the notion of a continuous time decision tree. Okay, this was introduced by people in computer science and originally used for discrete random variables. We adapted to the continuum, and this is one of the main technical contributions is to understand what is the right definition of a continuous time decision tree. So what is a first object is what is a stopping set? I call a set a random closed set a stopping set. It is allowed to depend on the Poisson point process. It's a random set that depends on eta. Remember, it depends on eta. So Z of eta belonging to a compact set K should be determined by the restriction of eta to K. That is, if I want to know my random set is inside a compact set, if I want to know if Z is inside K, I should know only the configuration of eta inside K. Okay? By just looking at eta inside K, if Z is inside K, what you do outside K is irrelevant. Z will still be inside K. To know that the random closed set is inside a compact set should be dependent only on the configuration inside a compact set. This is what is a stopping set. And the second property I need is, let me put, so this is 1, this is 2, 3. To avoid confusion, Z determines f of eta if I can tell the value of f by only looking at f inside Z. So remember, I cannot tell you the value of f by looking at any deterministic set, but maybe I can tell you the value by looking at choosing a smart random subset. I choose a good random subset and I can tell you the value of f. Okay. So f should be determined by restriction of eta only to Z. Okay. This is what I mean by Z determines f of eta. Now, what is a continuous time decision tree? I'm going to skip something. There are some technicalities. The point is I should get a sequence of stopping sets that increase to Z and are right continuous. And there are some more regularity. Okay. That is, they cannot have a lot of jump. They should not have jump discontinuity. That is, the volume of ZT cannot increase. When I go T to T plus, it should not increase. Okay. The volume should be negligible. Okay. So there are some regularity properties which we will avoid in the talk. Okay, but these are important. But the key thing is I should construct a stopping set in a sequential, in an exploratory manner. I should be able to explore a stopping set in time. I should come up with a sequence of stopping sets that increase to Z. Okay. And it's right continuous. Okay. And the next key object is what is called the revealment probability. Delta of Z is the supremum over all possible configurable points XR such that XR is explored by Z. What is the probability? Yeah.
Yogesh, can I please ask a question? Sorry for the interruption.
Yeah,
I'm confused here about what depends on what for this stopping set, because eta is your random configuration. So
yes.
Z is a functional of this configuration.
Yes.
How
yes.
much? Okay, and so together with the observation, you define a set. For instance, the convex hull. That could be an option.
Yes. Yes.
Okay, and then you say whether. Okay, yeah, thank you. I've got it. Sorry for the interruption.
No. Okay, so maybe let me give a simple example of a stopping set, and this is not a bad idea to do it. Okay, so let me take maybe, let's say origin is my point. Okay, let's say this is my points eta. I will say my stopping set is the ball. Okay, the first point I see in eta, starting from origin, I grow my ball of radius some r. Okay, my stopping set is such that I contain only one point, or there is no point in the interior of the stopping set. Okay, z is such that it's a random closed set, such that eta intersected z interior is empty. Okay, and starting from origin, z is a ball of radius, say r is random, such that eta intersected z interior is empty. Okay, so this stopping set is very easy to construct because from origin, I keep growing balls. Okay, the first time I hit a point, I stop. And I need to know only what is there inside. Okay, if I want to know that, if you want to know that is z inside a k, right, is determined by, this is equivalent to, if z should be inside k, it means that, you know, all I look is z intersection, this is true. I have to look at the configuration only inside k, because if there is no point inside k, k will be contained in z, and k contained. So this is what it is. If z is inside k, if and only if z eta intersection k is in k, I can even more easily write it as let me, I mean the, whether the ball, let's say, yeah, okay. So this is an example of a simplest example of a stopping set. The first point closest to the origin, the ball such that the boundary has the first point closest to the origin. Okay. So now just I will only have this revealment probability to emphasize that delta of z is the probability a given point and a radii is in z taken supremum over all possible points. Okay. All possible x and r. Okay. And remember x and r, they belong to Rd times 0 to R naught. Okay, R is bound, at most R naught. Okay, I look only in the support. Okay, so this is my revealment probability. It's the probability something is revealed by the algorithm. And now here comes the main inequality.
Sorry, Yogesh,
Yeah.
I have a question. What is the tree? I didn't understand. Where is the tree?
The tree is because you are exploring it in some way. Okay, it's called okay, I should be, let me clarify, even though we call it a continuous time decision tree, the name is inspired by, by computer science terminology. All it means is the way you explore it, there is some sort of a tree structure you can extract out of the exploration procedure. Okay, because here, for example, I'm just growing my sequence of balls little by little. Okay, this gives me a tree. I can build a tree structure out of it. It is not very straightforward, but not of relevance to us here. It's just a name for it. Okay, we just stick to the name. Yeah. So you can think of, all it means is that there is a way of exploring the stopping set should be explored. Okay, it's not that you just give me a stopping set. You have to have an exploration of the stopping set. Okay. So I'm not telling you why it is called a tree. There is a way of coming up with a tree based on this. In the discrete, it is more obvious. In the continuum, it is not so much clear. Okay. Sorry about it. Okay, so here is the main inequality now. The main inequality, which is called the OSSS inequality, I will say who are the 4 people in OSSS. Okay, we call it the Poisson OSSS inequality, is that give me a stopping set determining a function, give me a decision tree determining f of eta, and f of eta is in -1 to 1. Okay, it's bounded above by 1. This is important. then the variance is less than or equal to, look, it's 2 times lambda times the probability XR is in Z. The key thing is the decoupling. The Z and the difference operators are decoupled. The Z is here, the difference operator is here. These two are decoupled, and then it's exactly like the Poincare inequality. So this is separate from this. Okay, this is the important thing. And now you can take the supremum and easily get a delta Z. Remember, delta Z is the supremum over all XR. Okay, this is the important thing now. Okay, so very good. So variance of f of eta, I have improved the Poincare inequality by this extra factor, which depends on how good an algorithm you can come up with, or how good a stopping set. To me, I use the word stopping set and algorithm interchangeably. Okay, how good a stopping set can you come up with? Can I come up with a good stopping set and make this very small? Then I beat Poincare inequality. If not, I don't beat it. Okay, there are cases you don't beat Poincare inequality. We will see in this case, in the case of percolation, we will beat Poincare inequality significantly. Okay. Okay, some remarks. I'm not going to, due to lack of time, I will not be saying so much. There are improvements of Poincare inequality known as Log-Sobolev-Talagrand's inequality. If you do not know it, it is not important for the talk. But for the Poisson process, these are very restrictive. But even if the full L1, L2 or Talagrand's inequality is proven in full generality, these are still not good for our applications. Okay. And the OSSS inequality, this is the OSSS inequality, is proven in full generality of Polish spaces and Poisson process with diffuse measure. Okay, I have stated it, a version here. For the specific Poisson process, we are interested, but it can be proven for any Poisson process on a Polish space with a diffuse intensity measure. Okay. Okay, and here is a brief word on OSSS. It stands for O'Donnell, Sachs, Schramm, and Servedio. They proved in 2005 an inequality of variance of independent random variables. They proved it for variance of f of x1 to xn, where xi's are independent random variables. And it was, the use to percolation was pioneered by Duminil, Copin, Roffi, and Tasio, as I said before. And this is our motivation. We were inspired by this paper is when people realized the power of the inequality. Okay, so OSSS inequality is originally proven for independent random variables, where x1 to xn are independent random variables. You look at variance of this, and you have an algorithm exploring the random variables. Okay, so we have replaced the algorithm by a stopping set. In the discrete scenario, you have an algorithm. Okay, one by one exploring the random variable. In the continuum, we have a stopping set. Again, the important part is this inequality. Okay. So I will probably have a quick this thing about, I mean, I'll just again allow the inequality is important. Okay, we will now come up with, show an algorithm for the specific case of indicator. There is a path from origin to a ball of radius n. Okay, here is my Fn, here is our algorithm or a stopping set. Here is a stopping set. So my function Fn, remember, is the indicator. I have a path from origin to the boundary of a ball of radius n. This is Fn. Now, what is my Z? How do I construct a Z? How do I construct a Z? You fix a S. You fix a S in 0 to n. Look at the ball of radius S. Okay, I look at this ball. I look at the ball of radius S. Look at all the components of the occupied region. So I'm looking at all the components of the occupied region that intersect the ball of radius S. So in this figure, these are all these things. There are 3 components that intersect the occupied region. Okay. There are three components that intersect the occupied region. So I look at all of them, look at their union. So here I should have, call their union to be S. So S, capital S is the union of the components intersecting this intermediate ball, boundary of the ball. And now my ZS is S. I look at S, I blow it up a little. I look up at a blown up region around each S. I look up at a blown up region around each component. Okay. So that is, I have a region like this. This is my ZS. So I take each component, blow it up by radius 2r0, look at this new region. I call this ZS. I'm not going to tell you how, but ZS can be constructed as a CTDT, continuous time decision tree. I'm not going to explain this. Okay, it's technical. Why it can be done? You have to, think about how it can be done. Okay. When is a point X in ZS? This is crucial. This is the revealment probability. When is a point X in ZS? Is that the probability, the ball of, remember, if X is in ZS, a ball of radius 2r0 around X should intersect S. A ball of radius 2r0, that is, look here in the figure, let me draw maybe another point also to show this. Maybe a ball of radius X, and I draw a ball here. This is a ball of radius 2r0 of X. This should intersect S. Then only, okay, X can be in ZS. And then, again, I'm skipping some inequalities. But the key point is I can bound this by the probability there is a path from origin to S minus S to X. This, taking out some constants dependent on R0, I can bound this by this probability. Okay, I can bound this by the probability there is a path from origin to S minus X of 0. Okay, the distance between S and X. Okay, this is what it is. Okay, so this is uses FKG and some translation invariance. I'm not going to explain this. And this, by definition, is this. From origin to S minus X, this is what I get. This is still not good enough for me. This is still not good enough for me because it does not decay fast. Now here is the very cool trick. Choose an S in 0 to N at random and call Z to be ZS. Call Z to be ZS. Okay, this is a very cool idea that deterministically I have for a fixed S, this is the bound. Now choose a S at random and take a stopping set based on this ZS. And then what do you get is very neat is I average over this and divide by N. I take the average from, because I've chosen S at random, you integrate this over S and I have to divide by N. And now by just using a simple translation invariance, S is between 0 to, this integral is same as 2 times theta S of lambda. So the X vanishes. Now the X has vanished. The cool, this is a very easy thing that I can replace this by 2 times this. The integral is same as this integral. And that's it. And this is by definition Sn. Okay. So now my revealment probability I have bounded by 2 Sn. Okay. I know I think the time is over. Maybe in a minute or two, let me wrap up. I will just maybe give a quick sketch of proof and stop with that. Okay. So before that, maybe I'll take a minute and just say that the revealment probability, now we get what we want with the constants. So the inequality we needed is the inequality we have got. Okay. So I've got this inequality. Now, if you use the Poisson OSSS inequality, I've bounded the delta by this. So I get this term, exactly what we needed. Okay. So, I mean, some parts in the algorithm I know is not clear exactly these, but it's not a hard thing to work it out. But the key point is only this part, that you pick a random ball in the middle and look at the components intersecting this random ball. Okay. Okay, let me not spend, I won't say too much on the proof. You can find in the slides on the website. Okay, the proof goes by a very nice interpolation argument. Okay, this is what we want to prove. The simple interpolation trick is, every time I explore a region eta, I explore some Zn. Suppose I can construct it by a discrete sequence. Instead of continuous, take the restriction of Zn converging to Z. That is a discrete exploration procedure, not a continuum exploration, a discrete exploration procedure. Okay. Then whenever you explore Zn, you replace eta inside Zn by an independent copy eta prime. Okay, eta prime is independent copy of eta. So you replace inside Zn eta by an independent copy. Outside Z it is independent. You can say it is independent of eta. So you are slowly replacing a little by little eta by an independent copy of itself. And eventually, you go from eta to eta prime. And so, at time 0, you are f of eta, because inside Z you are eta. At time infinity, you have become eta prime. Everything has been replaced by eta prime. And simple triangle inequality tells you that you can use a triangle inequality and write it this way. And by doing a very infinitesimal analysis of this, the proof can be done. This is the idea of the proof, but the actual proof is a little different. Okay, we directly do an integral representation and make an equation and work with it. But this is the idea of the proof. Or the heuristic why this inequality should be true like this is that you can first break it up into this and try to understand that if Zn's become very small, then you get this structure. Okay. And you can express the variance in some terms like this. This is not too hard. To write to bound the variance by 2 times this. Okay. Let me not point out all the details, but see only this simple thing is here. If f is bounded by 1, if f of eta is bounded by 1, variance can be bounded by this. This is a very simple fact. Okay. So let me stop here for the first talk. In the end of the second talk, I might give jointly applications to some newer results in confetti percolation and K percolation. And if maybe not all will stay for up to the end, usual. But anyway, let me thank a lot of people who are also very crucial to this work. Rafael, who's here, and Hugo Vannevel, and then Laura and Sergei, Zuev, and Shrikant. Okay, so sorry for the extra time, and let me stop the first talk here.
Okay, so we can take some questions. If anyone would like to ask, can they unmute themselves?
Yeah, I have a question, Yogesh.
Yes.
So this stopping set argument. So it's a bit like you're saying you have the strong Markov property at stopping time. So now you are using sort of the spatial Markov properties, I guess.
Yes.
So this technique would apply also if your Poisson process would be replaced by anything that would have some nice spatial Markov property.
You're absolutely right, Frank. That's the thing in the decomposition we exploit here is the spatial Markov property.
Yeah.
Okay. So that is what you need is that what happens, the configuration inside the stopping set is independent of the one outside. So in general, you can ask for something like completely random measures or white noise or something like that. So if you have some white noise, then this kind of a thing can be, people use some way things like this. But in full generality, I don't think anyone has proven, say for completely random measures, it would be the most next interesting thing would be to show similar, ask for a similar inequality for a completely random measure. Okay, define a stopping set of a random measure and some functional of a random measure and for a completely random measure.
Yeah. Okay. Thank you.
Yeah.
And Yogesh, I'm Rahul.
Yes.
I know. I understand why you need your queue to have finite support, but can't you truncate to get this?
Okay.
Because of that compact ZS.
Okay, so we are unable to carry out a neat truncation argument at the moment. Okay, what Rahul pointed out is why do I need a compact support is this constant AR naught blows up when R naught goes to infinity. Okay, and I mean with Srikanth we have been discussing, Srikanth had something and we have been discussing with Srikanth to how to do the truncation. Okay, but I've not found a good way to do it. And even in Duminal Copa, Raufi, Tassion don't prove this, do the exponential decay via truncation. They use some renormalization and they don't go from OSSS via truncation. There seems to be some little obstacle there, but maybe I'm missing something. I'll be happy to discuss, later and see if we can do this. I mean, it would be great, but I do not know yet how to do the truncation correctly. I tried a couple of approaches, but I ended up getting stuck.
Thanks.
I'll maybe we can discuss later, Rahul. I would be happy to.
Sure.
Yeah.
Sure. Thanks.
Just a comment.
Yes, Robert.
Yeah, on the Markov set business, and there's an entire literature on sort of martingale sets and so on, stopping times, stopping sets. People like Elie Merzbach and Gail Ivanov, I think, even have a book on it. And so that will give a more, I mean, it won't help you in the Poisson case because there'll be weaker results, but there is an entire literature on stopping sets of that kind.
Okay.
So, I mean,
with a martingale stopping set, you mean with some notion of a martingale, but for sets?
For sets. So basically you have sets growing, which is what you have.
Yeah.
And then they stop at some time. There are stopping times, etc., etc.
Yeah.
So, I mean, it's what you've done in that specific case, but it's far more general.
So for the case of IID random variables, what you say is very interesting because for the case of IID random variables, the argument of O'Donnell, the OSSS argument is essentially the martingale difference representation of Efron-Stein, and then they carefully observe at some point you can say that the martingale difference matters only if your algorithm explodes the bit. So it uses the martingale difference referentiation. And it was, of course, Guenter who noticed that when doing in Poisson, you don't need to appeal to martingales. You can do it via Poisson calculus.
Yeah.
But what you say probably is very good for more general objects. It would be very nice if there is. I will look at it. Thanks a lot.
Any other questions? I have one. So just to understand, so this OSSS application, it looks like in here and mostly you have to construct a lot really you construct a lot of different stopping sets which are sort of disjointly supported. Then you randomize among them. This is the usual way of doing things, is it?
Yes. Okay, one technical again, sorry to, I don't want to confuse people more, is that the point is this is linear in this probability. The inequality, the first point, it is linear in the probability here. So this allows you to put additional randomness on Z that you can pick among many stopping sets and then average out here and still get it. So that's what is being exploited.
Yeah, of course, people must have wondered for this. So that suggests there may be another inequality which uses a sort of average rather than this average over space rather than this worst case over space of this.
You can't average over, okay, you can do various averaging, yes. What we do averaging is we are averaging over
Z, yes.
Z itself. I'm choosing based on S, I'm choosing different Z, but this is independent of my eta. The key point is that the averaging should be over an independent this thing. That is, you have some additional randomization.
Right. No, this way, yes, but I was just, no, it's very speculatively asking whether OSSS would have some sort of generalization where instead of the worst case that you have, there is an average.
No, but the first part is not the worst case. The more general is the first one. The first one is tight. There are examples where the first inequality is tight.
Okay.
The second one is not. Second one, I'm taking the worst case. But the first one, first inequality, if you think, is actually tight in some cases. We have explicit examples, very simple examples, like the simplest example of a stopping set I gave for the nearest point to origin or something like that. A modification of it will give you an equality here. Okay. But you can really consider various forms of averaging and so on because of the first equality.
Okay. Okay. Any other questions? So if not, maybe we start in at 3:35. Is that okay? That's only 8 minutes, Yogesh.
Yeah, that's okay with me. I'll just take 3 minutes and I'll be back.
Okay, so we will start at 3:35, which is in 8 minutes.
And I'll leave with the proof part. If somebody is still interested, they can look at it.
Yeah, Shiva announced it in the chat. The slides are available on the website, Yogesh website, Bangalore Probability Seminar. If you type, you'll find the slides are already there if anyone wants to see.
I'll be back in a couple of minutes. Okay, so okay, so now let us look at the second part. This is about noise sensitivity in continuum percolation and yet another inequality of Schramm, and this time with Steif. Okay. Okay. So for this, the broad philosophy or the thing I need apart from Poisson is a dynamics on Poisson point process. I want to keep updating my Poisson point process. Okay, so let me define a Poisson point process parameterized by time, okay, which changes dynamically. It's what is called the spatial birth-death process. It's an extension of the birth-death chain to space, okay. So what is it? Let me describe the simplest term is that, so given a Poisson point process, I keep each point independently of others with probability 1 minus e to the minus t. So I keep each of them independently with this probability. I denote it by this thing, 1 minus et, circle eta, which means that I keep some points, remove some other points. Points are removed with probability e to the minus t and some are kept, okay? And now eta prime is an independent copy of eta, and in eta prime, I keep each point with a probability e to the minus t. So I'm keeping each point in eta prime with probability e to the minus t, okay? And eta of t is nothing but a superposition of these two. Okay, that is, you delete points with probability eta to the minus t, sorry, e to the minus t. You delete points with probability e to the minus t from eta, and you compensate it by adding an independent copy with same e to the minus t. Okay, so this is this thing. Okay, so what one can show is that eta t is a Poisson process with intensity lambda. So let me make one thing here. This is a Poisson process. Poisson intensity will be lambda to the 1 minus e to the minus t. And this is Poisson. Parameter is lambda e to the minus t. Okay, so you deleted e to the minus t fraction of points and added e to the minus t new points, I mean, roughly on average. And by the property of Poisson process, these are independent processes. The sum is, if I superimpose both the points, take the union, this is a superposition or union, I get a Poisson process again, okay? So eta t is Poisson lambda. Okay, and one more point to add here is eta t is distributed as eta for all t. So eta t has the same distribution as eta for all t, and something specific, eta naught at time 0 it is eta, at time infinity it is eta prime. Okay, very easily observed. Okay. Oh, I think I got my time this thing wrong maybe. Yeah, I think I got my time. I should have. Sorry for the. At time 0, I want it to be eta. Yeah. Okay, I think now the time thing is correct. If I put t equal to 0, this vanishes, so it is eta. If I put t equal to infinity, this vanishes, it's eta prime. Sorry, I just did the e to the minus t and 1 minus e to the minus t wrong. Okay. Okay, so this is what it is. So eta t, I call it a spatial birth-death process. There is one little point I have not said correctly is I can realize eta t as a Markov process. It is not obvious that there is a Markov process satisfying this condition. Okay, I have only said that every time t, Rahul's question, is there a flavor of enhancement? Okay, I don't, yeah, it is some sort of enhancement, but you're also deleting things. But the enhancement argument will be useful to think that you're adding more points, forget the deleted points. This kind of arguments are useful, but I don't know how to say more than that. Okay. Okay. So at every time t, I have this distribution, but can I have a Markov process like this? Indeed, yes. Okay, I can convert it to a Markov process. How do I do it? Is that I will again describe it on a compact set, and the general thing you need some extra things, but here is the business in a compact set. Fix a compact set. What do we do? is each point as an exponential clock of rate 1. When the clock rings, the point will die. So each point has an exponential clock of rate 1. And when the clock rings, the point will die. That is, you remove the point. And newer points are born at the rate lambda times the volume. So I add new points at this rate. And what is the location of the new points? The radius clear, q, and xi prime is uniform. Very simple. So you have two competing exponential clocks. One is rate 1, one is lambda times the volume. Okay, when one clock wins, you pick a point uniformly at random and kill it. Okay, among all the clocks, and then you have a point being born at this rate. Okay, so every point has an exponential 1 rate of dying, and new points are born at this rate and dependent on the size of the window. And this way you can get a Markov process, and this semi-group is called the Ornstein-Uhlenbeck semi-group, but not so much important for the talk. We won't spend, I mean, it's the most natural thing you can do, but the important thing is this part, that eta t, I can get it by deleting some points at random and adding some new points from an independent copy. Okay. So this is what is important. What is noise sensitivity? That is, if I give you a 0, 1 valued function, fn of eta, a sequence, I give a sequence of Boolean functions. Okay. There's no question mark here. A sequence of Boolean functions. Is it true that for all t, fn of eta and fn of eta t are independent as n goes to infinity? That is, you do a very small, remember eta t means what? We have deleted e to the minus t points. Or you have preserved just e to the minus t points. So which means you have a small fraction of points, 1 minus e to the minus t fraction of points. When t is small, this is roughly like t. T points, roughly fraction t points, have been resampled. But does this make the two functions independent asymptotically? This is what is noise sensitivity. Okay. Now let's define this formally. So I call a sequence of functions fn of eta, taking values in 0, 1 to be noise sensitive, if for all t greater than 0, the covariance at time t goes to 0 as n goes to infinity. I call this covariance as nsn of t. This is the noise sensitivity at t. Okay. So this will be important. We will keep quantifying also t in terms of n later. This is, so nsn of t is the covariance of fn at time t with fn at time 0. And in n, this has to go to 0 for all t positive. This is noise sensitive. Okay, I don't know the exact origins, but I think it was by Benjamin E. Kalai and Schramm in 98, 99, something like that. If I'm wrong, sorry. Could be maybe a little earlier, but my guess is, my understanding it is by them, they introduced this notion. Okay. Now, another related notion to noise sensitivity. So noise sensitivity, you see, does not need the Markov property. All it needs is only at eta t to be defined at time t. It does not need Markov property. The next question, which is a more, you're asking something more, is, or slightly more, is that I look at the set of times where you get the Markov as your birth-death process evolves, your function keeps flipping. How frequently does your function flip? How frequently does it keep flipping? Okay, so I look at the number of times. This is called the set of exceptional times. Sn is the set of exceptional times. Because of stationarity, it's good enough to look in some fixed compact interval. Everywhere else, it is the same. Okay, so it's not a problem. So I just restrict it to 0, 1 for convenience. How many times in 0 to 1 does the function keep flipping? How frequently does it flip? And I won't discuss, but this is again to emphasize noise sensitivity implies a lot more, that somehow your function with very small perturbation becomes independent, tells you a lot about the function. Okay, it is very important because it now tells you something, in fact, something stronger. It tells you, for example, here is the result we prove, is that based on, of course, the argument of Benjamini, Kalai, and Schramm, adapting their arguments, is Fn is a 0-1 valued function, so I want it to be non-trivial. That is, it should not go to 0, it should not go to 1. It should be bounded away from 0 and 1. We call this non-degenerate. Okay, so this condition is called non-degenerate. Let me write here. Non-degenerate. Okay, when I say non-degenerate, it means the functions is neither 0 nor 1. And suppose at some scale Tn, ns n of Tn goes to 0, okay, for some bounded sequence Tn, then the number of oscillations in the interval Bn, which is slightly larger than Tn, Bn goes to 0, but slightly larger than Tn, okay? Okay, then this goes to infinity. This is called volatility. That is, you have infinitely many fluctuations even in a small interval. So all we have said is NSN, that is noise sensitivity at scale Tn plus non-degeneracy implies volatility. This is an argument of Benjamini, Kalai, and Schramm proven for critical percolation, but the same argument can be adapted for more general. And this is what we do here. Okay, I'm not going to say anything about this. One more consequence, you can get a variant of sharp phase transition by knowing non-degeneracy and noise sensitivity. Okay, so not the way I said before, but a variant. Okay, but let's not discuss too much about it now. I won't discuss the consequences of noise sensitivity here. I'll focus only on noise sensitivity now onwards. Okay, two very good sources. There is a book by Christoph Garma and Steif, and even better, much faster introduction is a very nice survey by Christoph Garma explaining Oded Schramm's contributions to noise sensitivity. And that covers a lot of noise sensitivity literature, at least a while ago. Okay, whenever he wrote it, a lot of it is covered in that survey. Okay, now let's come back to our old thing of stopping sets. Okay, again, I'm just recalling for if somebody, there is some new people, but it's anyway refresher on stopping sets. Again, let's get it right. A stopping set means that all I need is that restricted to the set K, eta intersected K should determine Z is in K or not. I need to know Z by dependent only on eta inside K. Then Z determines F means F should be determined by the value of the configuration inside the stopping set. I also have the revealment probability. Okay. So one thing, sorry, I forgot to mention before is that in the discrete case, usually stopping sets are, instead of stopping sets, the analog is an algorithm. That is, instead of a Poisson process, if you have IID 0, 1 random variables, instead of a stopping set, you have an algorithm that checks bits one by one, and the analog of a stopping set is set of bits revealed by an algorithm. Okay. Now, let me state the main theorem we have. Okay. This is our main result. It's actually much neater than even the one using OSSS, because I don't need, the big difference is I don't need the stopping set to be a continuous time decision tree. It need not be exploratory. Give me a stopping set somehow. You don't need to give it exploratory. You don't need to construct a ZT converging to Z, nothing. Just give me a stopping set. So I have a sequence of functions, 0, 1 valued. Assume that it is non-degenerate. Okay, that is for all n, expectation Fn is neither 0 nor 1. I have a sequence of stopping sets Zn that determine Fn. Okay. I have a sequence of stopping sets Zn that determine Fn. And now the revealment should converge to 0. The revealment probability should converge to 0. Then look at some Tn, look at a Tn such that delta n is less than 1 minus e to the minus Tn square. So let's put it here. This is roughly like order Tn square. Okay, when Tn goes to 0, this is like Tn square. Okay, so whenever Tn square goes to 0 slower than delta n, Tn square is going to 0 slower than delta n, then you get noise sensitivity at scale delta n. Okay, so this is like makes the proof of noise sensitivity, that is to show noise sensitivity, it is saying you need only two things: non-degeneracy, you need non-degeneracy, and then a smart stopping set. Okay. Okay, so you need a smart stopping set and non-degeneracy. At the moment, there is really one stopping set construction. So there was originally one smart stopping set construction, which all of us are adapting. And this implies quantitative noise sensitivity. Okay, that is, I know also not for every T also, I can allow T also to vary with N. So that's quantitative. It's telling the scale Tn. Okay, that is called quantitative. That's why we call it quantitative. Okay. And this actual theorem is actually a very easy corollary of what is the Poisson Schramm-Steif inequality. We will discuss this later. Okay, I will try to indicate Schramm-Steif inequality later. Very beautiful inequality. And the discrete proof, if you are, I mean, I'll present something about the continuum, but the discrete proof is a very nice argument using conditional expectations and so on. It's about half a page in Schramm's original paper and Schramm-Steif original paper, and I think that's the best exposition of the proof as well. Half a page or a page, yeah. Okay, now let's do the application. I will do applications and then go to Schramm-Steif inequality and give a proof of this theorem. This theorem can be proved fully using Schramm-Steif inequality. Okay. Okay, so let's give an application. So again, rehashing the slide on the Boolean model, recollecting the notation. I have a Poisson point process, that is xi are Poisson process, ri's are radius bounded above. Okay, ri's are all bounded above by some r naught. I look at C lambda to be union of all the balls centered at ri's at xi of radius. And remember, what did we show last time? In the last talk is that there is a lambda c such that above lambda c, theta lambda is positive, and below lambda c, theta lambda is actually 0. One little thing, I made a mistake here. Okay. Originally, it was in a later slide where that is true, but restricted to dimension 2. But now this is in this slide, it's not true. Next slide, the inequality can be made, the equality part can be added. Okay. So anyway, I have the occupied region. Okay, and then I look at the probability of going to a ball of radius s. We know as s goes to infinity, this decays and then decreases, and we said it goes to 0 and positive when lambda is greater than lambda c. I introduced a new event. Okay, the event is, now onwards I stick to 2 dimensions. Okay, the final results are known only in 2 dimensions. There are some estimates missing in a higher dimension. So I will just focus on 2 dimension for applications. So in 2 dimensions, because defining, I can draw the picture and define things. The first event is what is called the crossing event. Okay, this is the crossing event. And what is the crossing event? Okay, Roman's question is theta lambda always continuous. So I think it means that it's equivalent to theta of lambda is equal to 0. Theta of lambda c is equal to 0. So continuity is equivalent to theta of lambda c is equal to 0. And theta lambda c is equal to 0, I think is known in dimension 2 and the high enough dimensions. As per my understanding is there. I could be a bit wrong, but maybe, yeah, if someone is aware, they can add in. But as far as I understand, theta lambda is continuous everywhere else except at lambda c is shown. So it boils down to showing at lambda c, theta of lambda is equal to 0. This is not known in intermediate dimensions. So now I look at crossing event. Okay. Okay. So that is there a crossing? Is there an occupied path from the left to the right of a box of size L and K? I take a box, rectangle of size K and L. I want a left-right crossing. This is what is crossing for me. Arm for me is that I take a ball of radius R at origin. I want a path from inside the ball going to a, so this is of course R less than S, going to a bigger ball. Okay. That is a crossing across the annuli. You can think of arm meaning a crossing across an annuli. So arm is a crossing across annuli. Okay, like this, I need a path like this or something like this. This is a cross arm event for me. From the first result of exponential decay, actually one can show the probability of crossing. So I take now a rectangle, a long rectangle, kappa n. Well, it need not be long. You can take kappa to be anything. It can be long or short. So kappa n comma n. Kappa is some fixed positive number. Okay. So kappa n comma n. This probability of this crossing, right, always goes to 0. Okay, I have a probability, this kappa n, and this crossing goes to 0. Okay, so this is what I get, and this is a consequence of exponential decay, yet another consequence. Okay, now let's state our application. It really relies on a very recent, very nice argument of just a minute. Yeah, for some reason the scrolling was stuck for a minute. Okay, so the estimate we needed, the estimates we needed, remember we needed a smart algorithm. Okay, we needed a smart algorithm and non-degeneracy. Both of this was given to us somehow by a recent paper of Alberg, Tasio and Teixeira, okay, which said that there exists some A such that the crossing probability at lambda c, it's a lambda c here. I will, if it's not clear, let me put it lambda c. Okay. Okay. So the crossing probability is non-degenerate, what we needed. Crossing probability is non-degenerate, what we needed. Arm probability decays R divided by S. If you want to go from R to S, in other words, you think fixing a R and only varying S, okay, decays in S in polynomial fashion. Okay, this is important. So this was shown by Alberg, Tasio and Teixeira in 2 dimensions. I'll emphasize it's again 2-dimension. They prove it in much more generality. They don't need compact support. They can deal with unbounded support with second moment or something like that, 2 plus epsilon moments. Okay, that's all they need. And earlier results like this, I think Rahul proved one in his thesis, and then Alexander had a variant of this. Broadly, all of them using RSW theorem. Okay, essentially the key thing here is the RSW theorem, and all of them, both of them had variants of this in their works. Okay. Okay. And what we show now is, of course, given our main theorem, all we needed to do was to come up with a stopping set. And I'm now telling you, I'm not telling you the stopping set, I'm telling you the revealment probability delta n. Revealment probability delta n is bounded above by the arm probability integrated 0 to n constant by n. Okay. I missed some constant. Okay. If you want, you can put a kappa here, more explicit. So we can come up with a stopping set, which is an adaptation of the stopping set I gave in the previous talk, except now for crossing. Now I'm asking for crossing events. So indicator, there is a crossing. This function is non-degenerate because of this. This implies non-degeneracy. Okay. And now my smart stopping set, okay, is essentially having this probability. And now plug in the R by S to the alpha. R is, let me actually, one more small, how many typos one notices in a talk. It's a bit surprising. Okay. So, yeah. So this is R naught actually. That's all I wanted to. So the R, otherwise R is arbitrary parameter, but R naught is fixed. Okay. So R naught is fixed for us. S is the varying. So this decays like S to the minus alpha, integrated 0 to 1, you get overall a minus alpha. So essentially, if I take Tn to be n to the minus alpha by 2 plus epsilon, for any epsilon in a range alpha by 2, you get noise sensitivity of this scale. So you get quantitative noise sensitivity with this exponent. So we can exactly determine the exponents as well. I can tell you the exponent of noise sensitivity as well by this, our abstract result. So this was a question in a paper by Alberg, Broman, Griffiths, and Morris, where they showed noise sensitivity, not quantitative, noise sensitivity when the radii are fixed, not random, but fixed. And they said same thing should work for when radius are random and bounded support. Their proof is completely different and much longer. Okay, they use another result of which is of Benjamini Kalai Schramm randomized algorithm approach, which is very different to which is somewhat different to Schramm-Steif. Okay, so this is a point. So this is a nice application. So let me quickly make some remarks. So the assumption of ball was needed only to use Alberg, Tassion, Teixeira. So the general result will be non-degenerate plus arm decay probability implies quantitative noise sensitivity. Any dimension, shapes, everything. Non-degeneracy plus arm decay probabilities implies quantitative noise sensitivity. That's it. And we will talk about some generalizations later. Let's skip it. But the key point to note is this. Non-degeneracy plus arm decay probabilities, if you can show, you can get noise sensitivity by immediately applying our results. Well, what about the stopping set? Can you do it in general? Well, you will see it is not too hard. Okay, here is the randomized stopping set. I'll be more sketchy here. This is a crossing. Okay, so what do I do here? Now let me explain here. We pick S uniformly at random. So you pick a line. I want to know, is there a crossing? Right? I want to know, is there a crossing? I pick a line uniformly at random first in 0 to kappa n and look at the same thing, union of connected components that intersect the line. So I look at this union, I look at this union. Okay, I have these two. And then again blow it up by BR. And no, I can take here 0 to R naught. Okay, I take this set. That's it. This is my stopping set as before. Now I just take the line, look at all the components intersecting the line, blow these components a little, okay, and then I look at the product with all possible radii. This is my stopping set. That's it. If you tell me ZS, I know that whether I have a crossing or not, because I have explored the component intersecting the line, all the components. So if I have a crossing, it means that the component, there should be one component that touches both the left and the right sides. So ZS determines F, crossing. ZS determines crossing. And similarly, I can easily bound XR belongs to ZS is BRX intersection S is non-empty, which means from BRX, see here, from BRX, I have a path to S. a point X is explode. A point X is explode if BRX is, intersecting this line. Okay, there is a path from BRX to the line. Okay, and one more typo, R naught. Okay, so, and again, you can bound it exactly by the arm probability. You can bound this by the arm probability. And now average out over S. S is random. Average out over S and you get the result. Okay, so this is the arm probability, but S minus X. But if you average over all possible X, you get the result we want. Okay, so this proof is much simpler. Once you have the idea of the original randomized algorithm, there is nothing new here. Okay, it's the same algorithm, same, choose this line. I mean, it's really, as I said, the smart stopping set is originally only one. All of us keep following the same smart stopping set, is that choose somehow this line or ball at random and look at how many components pass through this. Okay, you have to find some blocking surface or a blocking thing structure to what you're looking for, and do that randomly and look at how many pass through this. Okay. Okay, now I will give some idea of the proof of Schramm-Steif inequality. Okay. Indeed, there are many things on the slide. Okay, and some are the middle parts, everything you can safely skip, not so much it's if you already are aware. But nevertheless, I want to emphasize two key ideas here. Is the chaos expansion for a Poisson process. People have used Schramm-Steif inequality or this randomized algorithm even for a Poisson models by using a lot of discretization, and it's technically much complicated. The main advantage we derive is by using purely Poisson calculus tools from Poisson processes, that we are able to come up with much simpler proofs firstly, and then much general. So let me take a Poisson process. I have a square integrable function. We know there is a chaos expansion. Okay. So what is a chaos expansion? Forget, if you do not know, all you have to think is F can be decomposed as random variables into a series of random variables. Okay, there is a series expansion for F in terms of random variables. These random variables have specific meanings. In interest of time, I'm not going to say everything. People who have seen it, it's a refresher. If you have not seen it, you can safely forget the explicit forms. All I mean to say is there is an explicit expression for everything here. Okay, these are all explicit, these random variables. These are called multiple Wiener Ito integrals, Ito kernels, all that. But the key property for us is two things. One, these random variables have an orthogonality property. These IK of UK, IKs have an orthogonality property. That is expectation of IK of U times IL of V. Okay, IK of U times IL of V is nothing but indicator K equal to L, K prime, lambda K UV. So the key is indicator K equal to L. So if K is not equal to L, the expected product of these two are 0. And for K equal to L, it's a L2 product of U and V. Okay. Okay, I should be a bit careful. One more typo. Unbelievable. I looked at it yesterday night and again today morning, but none of the typos were visible to my eye. It's the K, it's a K-dimensional inner product. Okay, it's a K-dimensional inner product. Okay, so taking a K, the key point is the orthogonality property of these IKs. And once you have the orthogonal property, then I can take f of eta times g. If I look at the covariance, you have this neat expansion where UK are the kernels for f and VK are the kernels for g. So I will only ask you to remember this orthogonality and, well, not remember, but keep in mind, this is the crucial point. Okay, this orthogonality is what is going to play the key role. Okay, and now comes the Schramm-Steif inequality. So after all that, the Schramm-Steif inequality is nothing but f of eta is I take a second square integrable function f, which is determined by a stopping set z. I mean, it's completely non-intuitive. It's not even clear why would you expect something like this. I mean, I still do. It's still a puzzle and a mystery to me, a complete piece of magic, that I'm looking at kernels, Ito kernels in the chaos expansion, and you can bound the squares. Okay, you can bound the squares by k times delta z expectation f of eta square. Okay. So you can bound the kernels by somehow coming up with a smart algorithm. You are able to control the squares of the multiple Wiener Ito integrals. Okay, by coming up with a smart stopping set. This is somehow a piece of magic, the original Schramm-Steif inequality. Okay, I'm not interest of time. I'll skip the proof. There is a one simple conditioning, conditional orthogonality, conditioning, and very clever analysis. I mean, the point is, if at all you are interested, read the original paper of Schramm and Steif for this conditional expectation argument. I will now explain how Schramm-Steif implies noise sensitivity and then say something about some new applications. So remember, I know the covariance structure for f of n with, I know how to evaluate the covariance formula, okay, in terms of the Ito kernels. Then when eta of t, you can explicitly compute the kernels. Eta of t, remember, is your dynamic process. You have killed e to the minus t points. Okay, you have killed e to the minus t points. Okay. Okay. So, or rather, you have not killed e to the minus t points. So you get this explicit expression using Mailer's formula. You can compute the Ito kernels for eta t. This is called Mailer's formula. It's proven by Last, Peccati, Schulte a few years ago. And once you use this, use the Poisson Schramm-Steif inequality here. So this is a very simple derivation from Poisson Schramm-Steif. And now it is very clear what to do. Fn are 0, 1 valued. Fn is 0, 1 valued. So this vanishes. Okay. So delta Zn comes out. You have a sum. So you have delta Zn e to the minus t, 1 minus e to the minus t squared. Okay. So NSN of t, I've got a quantitative control. We have an explicit bound, clean bound. Okay. This is the power of the Schramm-Steif inequality. Once you have it, you get this beautiful bound, which is easily studied. Okay. And the crucial other thing was Mailer's formula. And luckily I had two co-authors who were involved in proving it. So this part was easy to know that what was the right thing here. Okay. Okay. And minor remark, using Schramm-Steif, you can get a L2 version of OSSS, but this is not so useful. Okay, you get a square root here and a square here, all that, but okay, not completely useless because it applies in more generality, but square root and square restricts something. Okay, so this is the Schramm-Steif inequality. I know it's okay. So I'll use a few minutes, the last few minutes, to just describe two new applications. Okay. Whatever I've told you so far, application to the Boolean model. I mean, this is, of course, you know, some part is already known and some part, of course, we have simplified the proof, and some is new. Okay, the random radii noise sensitivity is new, but nevertheless, you know, what else can you do? You know, is this just going to go for Boolean model? Can I do something more? Yes, two applications. First one, I'll be much quicker because the results are less, you know, they are less concrete results. We give some conditions, and the same Boolean model I could have done with bounded random shapes. Instead of balls, I could have considered arbitrary random shapes. And then I can look at regions covered by not a single shape, but covered by multiple shapes. So I can look at regions covered by K shapes. Okay, that is, look at here. I look at regions covered by 3 shapes. Okay, regions covered by 3 shapes. I can look at this region and ask the same question. Okay, whether you get a sharp phase transition like OSSS, yes, you can do it. You can apply OSSS, this is okay. But non-degeneracy and arm probabilities, one has to prove. Okay, so I have not, I mean, to me, it appears that the methods of Albert, Tasio, and Teixeira should work even in this generality. But this has to be checked a little more. I'm not an expert in this, but yeah, I think their methods will work in this generality, and we should be able to get results for this model as well. This you can find in our paper, okay? And this also, some results are in the paper. It will come up probably in a month or so. Hopefully in a month, we will put up the paper online. And a more exciting result is what is called confetti percolation. So sorry about this. This is a little more, only people, if they know confetti, makes sense, else not so much. So in a confetti model, what do you have is, you have clouds of some shapes hanging at a height above the Euclidean space. The clouds are covered black and white. And from any given point on the plane, you look up, you see the first cloud you see, you take its color. So if the cloud above X is black, X is colored black, and you look at the black colored region of RD. So you place clouds at heights above the space RD. Okay. So you place clouds at height Ti above RD. All these are random. You color them black with probability P, white with probability 1 minus P. Okay. And then you look at all the points which see a black cloud. Okay. So you can ask percolation of this. This was introduced by Benjamini and Schramm. And this is a simulation when it's a disk P equal to half, 1/4. This is 1/4, half, and 3/4. Okay, as I increase P, it becomes black and black. And Benjamini and Schramm conjectured that when you take a fixed disk, when the clouds are fixed disks, the critical probability for percolation of OP should be P equal to half. Okay, it was shown by Tobias Muller in 2017. And we get the same result. Okay, we get the same result, but we don't need disks alone. You can take random shapes which are invariant under pi/2 rotations. Okay, so you can place random shapes invariant under rotations. That's the key thing. 90-degree rotations. Okay, so conjectured by Benjamini and Schramm, proven by Christian, proved it for the case of boxes, Muller proved it for balls, and Parthapratim and Rahul proved it for random boxes. Parthapratim and Rahul indeed use discrete OSS and discretization, and they do remark for more general shapes, but having this more general tool allows us to clean it up in one shot. And the last slide, essentially the same result I stated for Boolean model percolation. You can do it for confetti percolation simply because Albert, Tasio, and Teixeira have those results for confetti with disks. Okay. So, I mean, the point is that the moment you have this crossing and non-degeneracy and arm decay exponents, immediately you get quantitative noise sensitivity is the broad idea. Okay, so you can apply it in a variety of models, the same smart stopping set, everything is more or less the same. There are some technicalities, little minor things like some jump, Fn has to be jump regular, and which is a bit of, depending on your Fn, it can take a bit of effort to prove it, but otherwise it's okay. Okay, thanks.
Okay, so question time.
Yes, can I ask a question? I'm Rahul.
Yes, Rahul.
Yeah, for the D equal to 2 for K percolation, as you said, even the Albert, Tasio, and Teixeira, or the other things, they basically rely completely on the RSW formula, right? So,
Yep.
so I mean, for K, when K is bigger than or equal to 2, can you obtain an RSW, because it really requires degree of independence above and degree of independence below the path.
Right, because you will have, okay, when I went through briefly, at least I went through the introduction, and they say the few ingredients they require, right, for proving their estimates. Somehow it seemed they needed some sort of duality. So you look at K covered region and region covered by at most K minus 1.
Right.
Because you have a, I'm taking my grains to be bounded and all that. I was hoping there would be some, I can get some independence. But as I said, I might be wrong in saying that. I was discussing with Srikanth a bit, but we have not done much deeply. Because but when in their paper, if I remember, the things they said all seem to be true for K percolation. They needed some quasi-independence. Okay, they didn't need full independence. They needed quasi-independence, and then they needed FKG. They needed some symmetry and some invariance.
You also need
That I vaguely remember.
Right? And I think that will be the block. That is my.
Okay. Okay. Yeah, I would be happy to again definitely talk to you sometime on this once I understand their methods more carefully.
Sure, sure. Thanks.
I have a question. So this is Frank. So why Raoul, do you think that would be the block?
Because the RSW is required for the, in the Albert, Tassion, Teixeira, they require it to, they require it for exponential random, the radius random variable exponential. Okay, however, they truncate it and then use some kind of a Talleyrand inequality.
Mm-hmm.
Okay, and I think if you have two, the main way of defining an RSW is to go through the lowest crossing, right? In some sense.
Yeah.
But when you do the lowest crossing, because it's already K equal to 2, let's say, then you have a lot of information about what's above the lowest crossing.
Yeah. Yeah. Yeah.
That's why I think the RSW would be a block here.
Okay.
Yeah. I have another question which sort of returns to what I asked before. How much could you really get away from Poisson in your original model? Because you're in the continuum and you use this stopping set. I mean, it looks to me like it will not be easy to do anything beyond Poisson because you're in a continuum.
Okay. Okay. In the OSSS,
in particular, you can look on random cluster.
Okay, for OSSS inequality, Duminil, Coppa, Raufi, and Tassion proved a version of OSSS for monotonic measures. Okay, they used it to apply for random cluster measures. So by analogy, one would expect for positively associated point process or point process satisfying some monotonicity. Actually, some people have done it with discretization. I think Deredre and others do it with some discretization for some Gibbs model. It is expected that you can do for something more. And like what Robert said about these martingale sets and all that, maybe there is a hope. But when you come to Schramm-Steif, this chaos expansion is very crucial.
Yeah.
In the original Schramm-Steif, they again do it because OSSS is proven for independent random variables, whereas Schramm-Steif is already restricted to Bernoulli random variables.
You
use the Fourier-Walsh expansion. So which means, okay, for a white noise or a Gaussian random variables, you again have the series expansion in terms of the Hermite polynomials. You can hope to use it to derive something. This looks feasible. Okay. But more general, I'm not an expert in this thing of knowing for chaos expansions and stuff. I don't know how much general this nice structure you have and all that.
Okay.
So that is the main obstacle. I mean, at least the technique of Schramm-Steif is very reliant on this argument.
Okay, thank you very much.